My name is William. I'm a postdoc at Université d'Orléans in France. And I'm going to present our work on speech technologies with fieldwork recordings in Haitian Creole. So this joint work with Renaud Gauvin at Université d'État d'Haïti in Haiti, Benjamin Lecouteux in Grenoble, and Emmanuel Chong, my supervisor in Orléans. So if you have any questions about Creole, feel free to ask Emmanuel, who's in the assistance. So Haitian Creole is generally regarded as a low resource language. So low resource languages are often low resource only from the perspective of computer scientists, because there are actually many resources that were collected by linguists and the community of speakers across the years. So the only thing is that generally this data is not in a digital format, but exists nonetheless. So it's I guess not a proper term to call these languages low resource languages. So here in this work, we work with what I call legacy material. So it's archive data that has been collected quite some time ago. So here in our case, it's 40 years ago. That was stored in labs and our libraries. And so here the goal of our work is really to see whether we can train state-of-the-art speech processing models using fieldwork legacy material, so data that was collected a long time ago, and which consists of fieldwork recordings. So here we are testing the approach that was called Mobilize the Archives by Stephen Bird in his 2020 paper. So what do I call fieldwork data? So it's data collected for linguistic purposes, and that was not intended for computational applications. So it might be very noisy, and generally when in our specific case of working with legacy material is that it was recorded on tape recorders. So it has to be digitized first. That can introduce noise, and as you know, I guess fieldwork recordings are inherently noisy because of environmental noises, chicken, and so in the background. So it makes this data very challenging to work with, but it actually represents the majority of the data that is available for most of the languages of the world. So when we have data, it's more likely to be legacy material and fieldwork data. So, and here we focus on Haitian Creole, which is spoken in Haiti, so in the Caribbean, and is spoken by 13 million speakers, so it's really not a small language. It's mainly spoken in Haiti, but also in the United States by the Haitian diaspora. So it's a French-based Creole. French is called its lexifier language, which means that French gave Haitian Creole most of its vocabulary. So I'm just going to go through quickly on related works in speech processing for Creole languages. So the field is really sparse, except for a few notable works, which are actually all the works that exist. So specifically for Haitian Creole, there's been some attempt at building speech recognition by Breita in 2014 using Caldas style. A Caldas style approach. Recently, there's been a bit more work by Cécile Macaire in Grenoble and Eric Leferron in Grenoble and Orléans on Guadeloupean and Mauritian Creole. And there's slightly more work in Mauritian Creole by Mauritian researchers, but more focused on the medical domain. So as you can see, there's not much work that has been done on speech processing for Creole languages, so it's pretty unexplored. What is also important to us is to have also scientifically reproducible models available for these languages, and also monolingual models. So for French, for example, we have a French-based model called Le Benchmark. We also have English monolingual models, and here the goal is to build a monolingual model for Haitian Creole, and I could go into more details on why I think monolingual models are important, but maybe leave that for later. So here our assumption is that we have at our disposal fieldwork data that is potentially old, and our use case is build speech recognition tool for field linguists working on that language, or for a community of speakers that want to document their language. So our research questions. So can we use noisy fieldwork data to train state-of-the-art self-supervised learning models such as Wave2Vec 2, so for speech? Should we train these models from scratch, or should we use transfer learning and continuous pre-training? I'll go to more details into what is continuous pre-training. How much data is needed to fine-tune a model? And also something that is very important to us is, can we train these models on a budget? So let's say you have only one GPU. Can you train a good monolingual model for your language on one GPU and not 16? And because we work on Creole languages, what is the influence of starting from a model of the lexifier language, so here French, as opposed to starting from scratch or start from a model trained on another language? So a few words about continuous retraining. So the goal of continuous retraining is to resume the pre-training phase of your model, of an existing model with new and labeled data. So in our case, for example, it could be take a French Wave2Vec model and give that French Wave2Vec model data in Haitian Creole and resume the pre-training phase. So the pre-training loss function, etc. So CPT approaches have already been used for ANU by Novakovsky, also using all fieldwork data. The only thing is that they use 4 GPUs and XLSR 53, which is a pretty large model. And when they fine-tuned the data to do speech recognition in ANU, they also trained the model to transcribe in English and Japanese. So here in our paper, we aim for a structured approach using only fieldwork data at all steps, from pre-training to fine-tuning, with a linguistically motivated transfer. So starting from French model and comparing a model trained using continuous retraining and a model trained from scratch, what I call a monolingual model. So the data we use here is the Atlas Linguistique d'Haïti, which consists of 500 audio recordings, about 45 minutes each, in Haitian Creole. So the recordings were collected by Dominique Fattier between 1978 and the early 90s. For the purpose of creating a linguistic atlas. So a linguistic atlas, basically you ask people how they pronounce some words, or how do they call a given object. And they did that all around Haiti to map the dialectal variations of Haitian Creole. So it really wasn't sought as data to be used for computational applications. So they were originally recorded on audio cassettes and then digitized in 2010 by the French National Library. So it's also publicly and legally available. And to fine-tune our data, our models will use the corpus of Northern Haitian Creole by Albert Bandman, who recorded about 9 hours of Haitian Creole from Cap Haitien, which is north of Haiti. So it's really also fieldwork data. It's fully transcribed, but using non-standard impressionistic transcriptions. So for example, the capital city of Haiti is Port-au-Prince, which can either be pronounced Port-au-Prince or Port-au-Prince, depending on whether you use the French-based pronunciation or the more Haitian-based pronunciation. Or for question words, est-ce que with a very close vowel, or est-ce que with a more open vowel. So all the transcription capture those variation, and it really focuses on mapping the dialectal variation in Haitian Creole. So to test our models, we'll also be using 2 other data sets. So the first one is 80 CMU, which was recorded about 20 years ago now. It only consists of read speech, mainly from sentences and phrases from the Bible. And the more, and we'll also use the larger data set called Yarpa Babel, which consists of 200 hours of conversational speech on the phone. And we won't be using that data to train or fine-tune our model, but only to test our models on out-of-domain data, which is maybe cleaner than the data we have, to see whether our model are robust to out-of-domain data. So because of our low budget constraints, we use a wave-to base architecture and not a wave-to large. So base is 12 transformer layers instead of 24 for the large version, which excludes fine-tuning a larger model such as XLSL53, which is using the large architecture. So we use the Atlas Linguistique Deity for pre-training. So a few words about pre-processing. So we use a voice activity detection model to isolate spoken sections from non-spoken sections. So we went from a bit more than 300 hours of data to 200 hours. So it's a 35% shrinkage. So we use FirstSec to train the model, and we use a single GPU with gradient accumulation for 16 steps to simulate 16 GPUs. So all in all, it took about 1 month, well, 20 days to train each model. So regarding the models we trained, so the first one is what I call a native model. So we trained the model from scratch. That's why we don't have any base model. And we only give that model the data from the Atlas Linguistique Deity, so 200 hours of data. We also tried starting from a French model using continuous retraining. So that's the Le Benchmark wave-to-wake model. And we start from that model and give that model data from the Atlas Linguistique Deity. And we do the same thing with an English model. So it's what I call the foreign models with continuous retraining. And once we have these 3 models here in the middle, we are able to fine-tune them on the corpus of Northern Haitian Creole, so which gives us this model. So plus FT means fine-tune. So we have 3 models, one native that has only seen Haitian Creole, one that has seen French and Haitian Creole in continuous pre-training, and one that has seen English and then Haitian Creole in a continuous pre-training phase. And we also directly fine-tune the same models. So here we take the French model and we fine-tune directly that model on transcribing Haitian Creole, which gives us that model. So without any continuous retraining, and same for English. So in order to understand the effect of having various amount of transcribed data, we vary the size of the fine-tuning corpus from 360 minutes down to 5 minutes. So all the ASR model are fine-tuned for 20,000 steps, and the text is lowercase and diacritics removed. We also want to investigate the impact of having a language model to rescore the transcriptions outputted by the models. So we train 2 to 5 gram language models using only the transcription of the train split of the training corpus. So here we have, for example, 8 training splits, 360 minutes, 320 minutes, etc. So we train one language model for each training size, which gives us 32 different language models, depending on how many training data was used. So here are the results. So on the top table, it's sorted by word error rates, and on the bottom one, it's sorted by character error rate. So our best model is the model that is based on the French wave-to-wake model that has seen Haitian Creole in a continuous retraining phase and was then fine-tuned. So we have a word error rate of 36.8. And right after comes our native model, which has only seen 200 hours of data, whereas the French model has been pre-trained on 7,000 hours of data, so much more data. And then the English model. And regarding character error rate, the pattern is similar. First, the French-based model, then the native model, and then the English-based model. And the the best model are the ones that I've seen Asian Creole in the continuous pre-training phase. So just first conclusion here, it's possible to train competitive speech transcription models using a single GPU, using only fieldwork data, either at every steps of the way, so starting from pre-training to fine-tuning. So it means that we can successfully, repurpose all take recorded data for speech processing application, which is great for many languages actually. So one other question was, is it better to train the models from scratch or using CPT? So on the top row here, we have word error rate, bottom row character error rate. On the left-hand column, we have decoding without using any language model, and right-hand column using a 5-gram language model. So in orange, we have our native model for Asian that has only seen Asian, which is orange and dashed. In green, we have the English-based models that are based on the WaveCDec 2 base for English, and in blue, WaveCDec 2 French. So the solid line means that the model were trained using continuous retraining, and the dashed lines with diamonds means that the models were directly fine-tuned to transcribe Asian Creole without using continuous retraining. So, so is it better to train from scratch or use continuous retraining? Actually, when it depends on the amount of fine-tuning data you have, but when you have about 20 minutes of fine-tuning data, the difference is very minimal. And overall, continuous retraining is very useful. So as you can see, when you directly try to fine-tune the French-based model or the English-based model on transcribing Asian Creole, the error rates are much higher. So for example, here for English, than the model that has seen 200 hours of Asian Creole in a continuous retraining phase. So all in all, it's better to use continuous retraining, and it's yields a stronger model when you start from the French-based model, because it's the lexifier language of Haitian Creole. So regarding the amount of fine-tuning data that is necessary to have good transcription models, so as you can see, if you have less than 20 minutes of transcribed data, the native model is a bit all over the place, whether you consider word error rate or character error rate. So the foreign-based model that have been seen Asian Creole in the continuous retraining phase are more robust to that data scarcity in the fine-tuning stage. I guess it's because they have seen more speech during their own pre-training on French and English, which makes them better at modeling speech. But when you have 20 minutes of fine-tuning data, the gap closes. And as I said, when you directly try to fine-tune the foreign models, it doesn't work as well as using continuous retraining. As you can see, the dashed lines are above. And then should you use a language model or not? So basically, when you use continuous retraining, you basically don't need a language model, so the difference is quite minimal. But when you don't have continuous retraining data to pre-train your models before fine-tuning them, then having a language model helps getting better speech recognition. So here, for example, from the green English model, without using a language model, we have a word error rate of 60, whereas when we use a language model, the word error rate is of 50. So it's pretty dramatic, a pretty dramatic difference. So, and finally, we wanted to compare ourselves with MMS, so the recent model by Facebook. That was also trained to transcribe Asian Creole. And we tested it on our Fieldwork recordings. So that would be the top row here. And on the two other data sets that are more easier, it's red speech, or it's less noisy. So the MMS is not as good as our models on Fieldwork data. So there's a 10 points difference between our models and MMS. So it's a pretty huge difference. Whereas our models are pretty robust to the data set change. So MMS is better. So MMS has a 7 CER score, whereas our best model is 9. And for this data set, the difference is also pretty low. So actually, our models are pretty um, powerful, and especially when we take into account the fact that the native model has only seen 200 hours of training data, as opposed to MMS that was trained on much more data. So here we trained wave-to-wake models for Haitian Creole, and we focus on extrinsic evaluation of the pre-trained model using ASR, but we would like to understand the representation of these models using ABX tasks. So we use data that was collected 40 years ago, but we know that the language has changed from the language spoken in A now is different, at least for some points. So we need to evaluate the impact of language evolution. And we still use a lot of data, so 200 hours of data is still a lot, and we would like to explore the minimal amount of data we can use to train a good enough model for transcription. So as a conclusion, so we used old tape recorded fieldwork material in Haitian, and we successfully trained monolingual wave-to-wake models for Haitian Creole. So that demonstrates the feasibility of training self-supervised model using only fieldwork recordings at every step of the way, starting from pre-training to fine-tuning. And it shows that our methodology is applicable to actually any language that has old fieldwork legacy material. So, and our work finally supports the fact that the mobilizing the archive approach mentioned by Stephen Bird in his 2020 paper is a good way to go forward to design models for under-resourced languages. And finally, this work was supported by the Agence nationale de la recherche in France, and we use various computing clusters, Quetzalcoatl and Quasimodo. And yeah, I'm done. Thank you.
All right. Thank you very much for this wonderful presentation, William. We have 4 minutes for questions. So please, those on Zoom, if you have questions, you can put up your hand on mute and ask, or you can equally type it in the chat and I'll read it out.
I have a question. And you may have covered this and I spaced out, but at some point you were saying it was doing better with field data versus clean data, which is the opposite of things I've seen not in speech technology, but in other. So I'd like to wonder if you could expand on that a little bit.
Sorry, I didn't get that. Can you repeat your question, please?
Yeah, I was wondering if you could talk a little bit more about you were saying that it did better with field data rather than clean data.
Yeah. On the MMS slide. Here, that one. So actually what I wanted to say is that our models, despite being trained on very noisy data, noisy fieldwork data, transfer pretty well to clean data, which is not the case for MMS, which has, I guess, seen more clean data and not so much noisy data, which explains why MMS is lags behind our models. I'm not sure I answered your question. I didn't hear it properly, but.
Thank you. Yeah, that helps.
Any other questions?
So thank you for the wonderful work. I'm wondering, how do you incorporate the language model during the decoding? It directly affect the beam search process, or you rescore the in-fast hypothesis later?
So yeah, for the language model, we use basically rescoring with a beam search of 5.
So can you be clear, like you rescore the generated hypothesis that is generated first, or it is incorporated during the unbiased generation process?
So it's incorporated at each step of the decoding step.
Sorry, we're struggling to understand you a little bit in here. Microphone's not coming through clearly. Maybe. Yeah, maybe you're having trouble hearing us, so maybe if you have it on Zoom, you can chat. I can.